So what is discrete category? It is, by definition, a category whose only morphisms are identity morphism. Because by definition, a category for any object X, at least your home set should contain the identity morphism. And which is not necessarily a map, it's just satisfy the property that this composition with whatever other home is itself. Okay, anyway, when X doesn't equal Y, this means that the definition of the discrete category, the home set is empty. So let's come back to our product. So what is the case? J is discrete category. Our diagram is from J to category C, where we want to define what is a product. And so your J is just a category with objects as X, Y, Z, etc. And a diagram would be just this functor F maps objects of J to objects of C. That's how it's indexing. How it's indexing objects of C. And now, what is con? Recall con is an object of C such that a morphism is given for each object of J under the functor F. So Cx, Cy, Cz map to Fx, Fy, Fz, if X, Y, Z are elements of J. And so to be a con, you have to satisfy the commute diagram. So if you got Fx, Fy for whatever X and Y, then you have to check this Cx, Cy commutes is the morphism. But here, if X doesn't equal Y, then this is empty, nothing to check. This is not even a diagram, nothing to check. So just tell you there is a collection of morphisms. But if X equals Y, you may feel strange, but how do I check this is identity? Because F identity is again identity. How do I check this diagram commutes? But we're not saying for any morphism from N to Fx. It is for that given collection of morphism. So for each object X, there is only one morphism given Cx. So actually this is trivial. Still nothing to say. No more information. They just tell you there is a morphism from N to Fx. So this is the situation. And now we want to define a coproduct. Products to be a con that satisfies universal property. So the situation is as follows. Nothing to check, just a collection of morphisms, but put an arbitrary con further, which means it also has morphism, a fixed morphism, whatever it is, X, Cy prime, then it must factor through your universal object. This is called product. Okay. I'm not talking about product of 2 elements, I'm not talking about product of 3 elements, I'm talking product in general. Don't be confused with fiber product, which is defined here. We will say it is a more specific situation. Let's say third example, equalizers. If J is a category with 2 objects and 2 parallel morphisms from one object to the other. So J is very precise. It has only 2 objects, 2 parallel morphisms from one object to the other. The diagram of shape J is a parallel morphism in CP colimit. It will be, so if J is like this, then what you got is a map from J to F. this is what you have. This is a cone. And so a universal cone would be, let's call this F1, F2. Universal cone would be, let's call this C1, C2. Whatever object you put it further, let's just put it further as we just right here. You factor through U. Now this is called co-equalizer. Sorry, equalizer. The limit of such diagram is called equalizer isomorphism. For example, it's very abstract. For example, a kernel is a special case of equalizer where one of the morphism is zero map. So let's look at the example. So if you got first map zero morphism, why is zero morphism? One is, let's call it F, and then let's map it to C through the diagram. Their object make this commutes, which means this is object of C, such that there exists a map C1, C2, such that both diagram commutes, which means C1 0 compose C1 equals C2, and then still call it, just call it F, simplified notation. F compose C1 equals C2, but this is also 0. This is just saying that, so this is just 0 in this case. It's just saying that, let's give it a name, call this X, call this Y. You have a morphism from X to Y, call this F. And then you have a morphism, call it C1, such that the composition gives you 0. Right? That's all what it says. And now what is the universal property? Tells you that if you have another one object J such that this diagram commutes, which means again this J is also a map to X through some C1 to down, and this composition is also 0. And then the universal property is, and it factors through it. This is exactly how we know the universal property of a kernel. So you have a morphism, and if you have an object which map into X, composition with F equals 0. And the universal property says any other object composed with F equals 0 factors through this object. Then this is the kernel. Okay. Finally, let's say this. Pull back. The FB diagram then picks out 3 objects, X, Y, Z, and C. Okay, so we're the only non-identity morphism. So here we just make it, frankly, we don't start with J, so we don't care what happened on J. We just, actually, as you say, we just care about what is the diagram. So in this time, let's just say that my diagram looks at the follows. I have only 3 objects indexed. One is called x, one is called y, one is called z. I have to make certain diagram commutes, and I say my only diagram except non-identity, because the identity morphism is trivially make the diagram commutes. Okay, I have my px, pcy, pz. The only non-identity morphisms are one is called f, one is called g. And so this is my cone. The all diagram or commutes. And in that case, actually you could just remove this phi z, because phi z is defined to be the composition of these f with px or either j with cy. That's your phi z. And then universal property would be whatever. Put it further. Objects satisfy the same commuting diagram, and there is also pz prime, but again this pz rho prime will be composition of these two, or composition of these two, so I don't put it. Then there is factorization. This is exactly how we define fiber product. This is called the pullback. For me, it's always confusing why this is called pullback compared to push forward. Those terminology sounds very confusing. But pullback, you could think of, you got this free and then you just pull it back here, because the direction is kind of, you pull things back. Or in other words, you're starting with kind of a target of arrow, and you want to define what is the source of the arrow. It's kind of the direction is reversing. I guess that's why you call it pullback. Not quite sure. Okay, so we have, say, example of colimits, limits, and correspondingly we could have examples of colimits. Okay, there are still 2 more examples. One is called the inverse limit, is also an example of limit. Okay, that's something also very confusing in the sense of terminology. You define what is called limit and colimit, but as an example, you have what is called inverse limit and projective limit, inverse limit and direct limit. And even both of them have 2 names. So inverse limit the same as projective limit, and direct limit the same as injective limit. So those terminology really make things not that friendly. Okay, so let's see one more example. What is inverse limit? Inverse limit is again a particular choice of your category J. If you choose your category J to be direct, T is set. Or consider it as a small category by adding arrows. Arrow to J if and only if I is bigger or equal than J. I let F the diagram from the opposite of category of J to category C. Then the limit is called inverse limit or projective limit.